Let's talk about solving systems by graphing. There are three main steps we consider when we want to solve a system using the graphing method. You want to solve for y. So in some examples, when you already have two lines that are already equal to y, this would be your best method to use because they're already ready to graph. The second thing you want to do is graph both lines. You can either graph them by hand or with your calculator. And the third thing is to find the intersection of the two lines. So you can either do that by hand, by plotting and figuring out where they touch on a graph, or in your calculator, you hit second, trace, number 5 is intersection, and then you hit enter 3 times to get the answer. So let's look at some examples. Actually, before we get to the examples, I had one more thing to talk about. There are 3 possible outcomes when you're solving by graphing. The lines could be intersecting, like I have over here in blue, where they touch one time. So they have one solution, which is what I put in red right there, right where they touch. And they have different slopes, different y-intercepts. They're just 2 different lines, and they will touch in one place. So they're intersecting. Parallel lines is another option. These have no solution because they don't touch. They never will touch. They have the same slope, but notice they have a different y-intercept. So parallel ones have no solution. And your third possible outcome is sometimes you end up with coinciding lines, is what we call these. And they are when we have infinitely many solutions because they touch everywhere because they are the same exact line. So sometimes you'll be given 2 lines that don't quite look the same, but once you solve for y, you'll realize they really are the same line. But we do graph them. We put a little squiggly line to represent the second line is right over top of the first one, and we call these coinciding lines. And again, they have infinitely many solutions because they touch everywhere. So now let's look at a few examples. All right, so we want to solve for y if they're not already equal to y. For the first example, I gave you one that's already equal to y. And so when you see one like this is definitely an ideal method to use. So I'm going to use blue for my first equation. I'm going to start with the y-intercept at -2. So I go down 2 and put a point. Then I have a slope of 1. There's an understood 1 in front of x, which is like 1 over 1. So I need to go up 1 from -2 and to the right 1. And I can do that a couple of times to have a nice sketch of my line. All right, so then I'm going to use red for the second equation to make it stand out nicely on my graph. So I'm going to go up 7 for the y-intercept. So 1, 2, 3, 4, 5, 6, 7, right up there at the top. And then -2 over 1 is my slope. So I go down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1. And that helps me sketch a nice line for that second equation. And now I can see where they touch, and that's my solution. So my solution would end up at 1, 2, 3, 3, 1, which looks great. But you can also check your solution to make sure it's great. So I'm going to plug in 3 for my x and 1 for my y, because that's what those numbers represent. 3 is x and 1 is y. Back into the equations and check my answer. So y equals x minus 2 was my first equation. So I'm going to say y would be 1. Is that equal to 3 minus 2? And yes, 1 is equal to 3 minus 2. In the second equation, let's plug it in as well. So we have 1 for the y, -2 times 3 for the x plus 7. So is 1 equal to -6 plus 7? And the answer again is yes. So when you're checking your answer for a system of equations, you want to plug the solution into both of the original equations or however many you're given, but usually it's 2. So let's try another example. 3, 1 was our solution. Oh, and let's add one more thing to that one. These were intersecting, just to refer back to what we just saw. They're intersecting. They had one solution at the point 3, 1. So x was 3 and y was equal to 1. For example 2, we need to solve for y. So I'm going to take the first equation and solve for y. So first I'm going to subtract 2x. I'll bring down 4y. 2x goes away, equals -2x plus 12. Then I need to divide everything by 4, so y would equal negative 1/2 x plus 3. All right, so I can graph that one now. I'm going to put it in the same color on my graph. So I'm going to go up 3, then I'm going to go down 1, right 2 a couple of times, and I can go up 1 and left 2 to have a nice sketch of my first line. Now I'm going to solve the second equation for y. This one doesn't take much work because I just have to subtract the x. So I get y equals negative x plus 2, and keep in mind it's like a negative 1, so that's negative 1 over 1 when I'm graphing it. So let's put that one on the graph. We go up 2 for the y-intercept, and then down 1, right 1 a couple of times. And I can also go up 1, left 1, and then I see where they're going to intersect up there toward the top. So I end up with an intersection at, let's see, negative 2, 1, 2, 3, 4. Negative 2, 4. So negative 2 is the x and 4 is the y. These are also intersecting like the first example was. So let's add that to our notes. That's an example of intersecting. They had one solution at negative 2, 4, and you can plug them back in to check your answer. You would do just what I did right here, but I'm just not going to do that part for this example to save some time for the video. But you could plug in x equals negative 2 and y equals 4 back into both of the original equations and just check and make sure that that makes sense. But let's move on to 2 more examples. So for example 3, we need to solve for y. So let's take the first equation. I'm going to keep my color scheme going, so it's going to be in blue. We need to subtract x, so we get 3 minus x equals 4y, and divide everything by 4. So we end up with y equals 3/4 minus 1/4 x. Now if you don't like the y over here on the right, we can just switch it to the left. So we could say y equals negative 1/4 x plus 3/4. So then it looks like slope-intercept form, like what we're used to. So now I'm going to plot it on my graph. So I just go up 3/4. So it's up like almost 1 box, but not quite. So up 3/4, then down 1. So down 1 and right 4 would be about right there. And I could go up 1, 1, 2, 3, 4 to the left. So I sketch my line. I just don't have a ruler handy. And then for the second equation, let's solve for y. So first thing I could do, well, we just have to divide by 4, and we'll have y all by itself. So y equals negative 1/4 x plus 3/4. So now, you notice they are the exact same line. So this is the kind that's called coinciding. And in order to represent the other line, because we can't just graph it twice, we just put a little squiggly line. So I'm going to put it in red, but they're the exact same line. So this one we call coinciding. And this one has infinitely many solutions. So I'm going to keep my color scheme. Infinitely many solutions, because it would be any point on that line. You don't say that it's all real numbers, because it's not just any old number anywhere, it's any point on that line. And since that line continues on forever and ever in both directions, that's why we say it has infinitely many solutions. Now let's look at one more example, our last one. So I'm going to take the first one and solve for y. So 3x plus 6y minus 12 equals 0. We'll go ahead and add 12. So 3x plus 6y equals 12. Let's subtract 3x. So we get 6y equals negative 3x plus 12. Then let's divide everything by 6. So y will equal negative 1/2 x plus 2. All right. I'm going to graph that one. So I'm going to go up 2, then down 1, right 2 times, and then up 1, left 2 a couple of times, and then I have a nice sketch.
Good morning, teachers. If you have any questions regarding EVOS roster,
I'm going to take the second equation and solve for y.
Mr. Burleson in the Media Center at this time. If you have any questions
Subtract x.
regarding EVOS roster verification, please see Mr. Burleson.
So I've got negative x plus 8 equals 2y. I just need to divide everything by 2. So y equals negative 1/2 x plus 4. So let's graph that one. So I go up 4, 1, 2, 3, 4, down 1, right 2, using my slope. I can go up 1 and left 2. So what I notice is they look like they are parallel. And when I go back to my equations, I can see that their slopes are the same. So these lines are parallel and they have no solution. We can also represent that with a big 0 with a slash through it. So no solution. And they are parallel. Those two things go hand in hand. And so there's no solution we could check. In other words, no x or y would work with both equations because there's no point they have in common and no point where they will touch.